Preparing for a data engineering at Confluent interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What is Apache Kafka, and why would a company choose it for event streaming? Apache Kafka is a distributed event streaming platform built around durable, ordered logs. I would choose it when multiple producers need to publish events independently and many consumers need to process or replay those events at their own pace. Topics provide logical separation, partitions provide parallelism, and replication provides fault tolerance. Unlike a traditional message queue, Kafka retains records after consumption, making it useful for analytics, monitoring, event-driven services, and rebuilding downstream state. While answering, focus on Kafka's distributed commit log model, durable retention, partition-based scalability, producer-consumer decoupling, replayability, and how event streaming supports real-time applications and data integration. Question 2. How do Kafka topics, partitions, and consumer groups work together? A topic is a named stream divided into partitions, and each partition is an ordered append-only log. Producers choose partitions through keys or partitioners. Within a consumer group, each partition is assigned to one consumer at a time, allowing parallel processing without duplicate work inside that group. Adding partitions increases throughput, but ordering is guaranteed only within a partition. Therefore, I choose a stable business key when related events must remain ordered. Make sure to cover topics as logical streams, partitions as units of ordering and parallelism, consumer groups as coordinated workloads, one consumer per partition assignment, and the trade-off between scalability and ordering. Question 3. How would you choose a Kafka message key? I select a key based on the entity whose events require co-location and ordering, such as customer ID for account activity. That ensures all events for one customer reach the same partition, which simplifies stateful processing and joins. I would test the distribution because a highly active customer can create a hot partition. I also avoid changing key semantics casually, since repartitioning can alter ordering, load balance, and downstream state. In your answer, talk about business-level ordering requirements, partition distribution, hot key risk, null key behavior, key stability, stateful processing implications, and how key choice affects joins and consumer scalability. Question 4. What delivery guarantees does Kafka provide, and how would you achieve exactly once processing? Kafka commonly supports at most once, at least once, and exactly once semantics. I achieve exactly once within Kafka by enabling idempotent producers and transactions, then atomically committing output records with consumed offsets. However, an external database or API can still produce duplicates unless the sink supports transactions or idempotent writes. In practice, I combine Kafka transactions with deterministic event IDs, deduplication, and clear failure recovery, rather than treating one configuration flag as a complete guarantee. Be sure to mention at most once, at least once, and exactly once semantics, producer idempotence, transactions, offset coordination, external side effects, and why exactly once is a system-wide design property. Question 5. How would you diagnose consumer lag in a production Kafka system? I start by locating lag by consumer group and partition rather than looking only at an aggregate number. Then I compare incoming rate with processing rate, inspect consumer CPU, memory, garbage collection, downstream latency, rebalance frequency, and broker request metrics. A hot partition may indicate poor key distribution, while uniform lag may require more consumers or faster processing. I would also check deployment changes, pauses, throttling, and whether lag is growing or recovering. Focus on measuring lag by partition, identifying whether producers or consumers changed, checking processing latency and rebalance activity, examining broker health, and separating temporary spikes from sustained capacity problems. Question 6. What is the difference between Kafka retention and log compaction? Retention removes records based on age or total log size, so it is appropriate for event history with a defined replay window. Log compaction keeps the latest record for each key and eventually removes older versions, making it useful for change logs, configuration, or current account state. A tombstone marks a key for deletion. Compaction is not immediate, and it does not preserve complete history, so I select it only when latest state semantics are sufficient. In your answer, distinguish time or size-based deletion from key-based compaction, explain tombstones, describe suitable use cases, and mention that compaction preserves the latest value rather than every historical event. Question 7. How would you design a reliable data pipeline using Kafka and a cloud data warehouse? I would ingest validated events into appropriately partitioned Kafka topics, attach schemas, and use a managed connector or stream processor to load the warehouse. The pipeline should preserve offsets, support retries, route malformed records to a dead letter topic, and make warehouse writes idempotent through event IDs or merge keys. I would monitor lag, throughput, failure rates, freshness, and schema changes. Kafka retention provides recovery if the warehouse is temporarily unavailable. Cover ingestion, schema validation, partitioning, buffering, batch or streaming delivery, replayability, dead letter handling, idempotent loading, observability, security, and recovery from warehouse or connector failures. Question 8. What are Kafka Connect and Kafka Streams, and when would you use each? Kafka Connect is a framework for moving data between Kafka and external systems through reusable source and sink connectors. I use it for standard integrations such as databases, object storage, or warehouses. Kafka Streams is a Java library for application logic, including filtering, aggregation, joins, windows, and state stores. If the requirement is simple movement, Connect is preferable operationally. If it requires business transformations or stateful processing, I would choose Streams or Flink. Make sure to explain Kafka Connect's source and sink integration model, Kafka Streams application-level transformations and state, operational simplicity, custom logic requirements, and when a connector is preferable to bespoke code. Question 9. Explain change data capture and how you would implement it with Kafka. Change data capture publishes database changes as events, usually by reading the database's transaction log rather than repeatedly polling tables. I would capture an initial snapshot, then stream inserts, updates, and deletes with primary keys, operation types, timestamps, and source positions. Downstream consumers can build replicas or warehouse tables using idempotent upserts and tombstones. I would validate ordering, transaction boundaries, schema evolution, and recovery because CDC correctness depends on source log semantics. Discuss transaction log-based capture, insert, update, delete events, ordering, snapshots, schema evolution, primary keys, Debezium-style connectors, downstream upserts, and the difference between database polling and log-based CDC. Question 10. How would you handle schema evolution for events shared by many teams? I would use a schema registry with compatibility rules and treat event schemas as public contracts. Adding an optional field with a sensible default is usually backward compatible, while renaming or changing a field's meaning is risky. Producers should validate schemas in C, and consumers should test representative old and new messages. For major semantic changes, I prefer a new event version or topic rather than silently altering an existing contract. Focus on explicit schemas, compatibility modes, backward and forward compatibility, optional fields, defaults, versioning, review governance, consumer testing, and avoiding breaking changes in shared event contracts. Question 11. How do Kafka transactions differ from database transactions? A Kafka transaction can atomically publish multiple records and commit consumed offsets across Kafka topics. A database transaction provides atomicity within participating database operations. They are not automatically one distributed transaction. Writing to Kafka and an unrelated database can still fail halfway. I would use Kafka's read committed isolation for transactional records, an idempotent sink, an outbox pattern, or a coordinated connector when external side effects must be reliable. Be sure to compare atomicity boundaries, distributed participants, offset commits, isolation levels, external systems, failure recovery, and why transactional guarantees do not automatically extend across Kafka and arbitrary databases. Question 12. What is event time, and why are watermarks important in stream processing? Event time is when an event actually occurred, while processing time is when the system handled it. For accurate analytics, I generally aggregate by event time because network delays can reorder arrivals. A watermark estimates that earlier events are unlikely to arrive, allowing a window to close. I would configure allowed lateness and corrective updates based on business needs. Earlier results reduce latency, but waiting longer improves completeness and late event accuracy. In your answer, explain event time versus processing time, out of order and late events, watermarks as progress estimates, window closure, allowed lateness, and the trade-off between latency and completeness. Question 13. How would you design a streaming join between two Kafka topics? I first define the join key and whether the relationship is time-bounded. For two event streams, I would use a windowed join, ensure both sides are partitioned by the same key, and retain state long enough for expected arrival delays. For a relatively stable reference dataset, a stream table join may be simpler. I would specify behavior for unmatched and late records, monitor state growth, and consider repartitioning costs before implementation. Cover join key alignment, co-partitioning, event time windows, state stores, retention, unmatched records, late arrivals, repartitioning costs, and the distinction between stream and stream table joins. Question 14. What is stateful stream processing, and how do you make state fault tolerant? Stateful processing maintains information across events, such as counts, balances, or join buffers. I would partition state by the same key as the input, store it locally for performance, and rely on replicated changelogs or checkpoints for recovery. The design must bound state with windows, retention, or cleanup policies. I would test restoration time and monitor state size because a logically correct processor can still fail operationally if recovery is too slow. Mention aggregations and joins, local state stores, changelog topics, checkpoints, restoration, partition ownership, state growth, repartitioning, and operational planning for recovery time. Question 15. How would you prevent duplicate records in an event-driven data pipeline? I assume duplicates can occur because retries and consumer failures commonly produce at least once delivery. I would assign a stable event ID at the source, then make consumers idempotent by storing processed IDs or using deterministic upserts. Kafka transactions can prevent duplicate Kafka outputs, but external writes still need sync-level protection. I would define the deduplication window, account for storage cost, and monitor duplicate rates so unusual retry behavior becomes visible. Focus on the difference between delivery and processing duplicates, stable event identifiers, idempotent consumers, transactional boundaries, deduplication state, upserts, retries, and observability for duplicate rates. Question 16. How would you secure a Confluent Kafka deployment? I would secure transport with TLS, authenticate clients using certificates, OAuth, or another supported mechanism, and authorize access through least privilege ACLs or RBAC. Producers should write only to approved topics, while consumers should read only required topics and groups. I would place services on private networks, protect connector credentials in a secret manager, enable auditing, and test credential rotation. Security also includes controlling schema, environment, and administrative access. Be sure to cover TLS encryption, authentication, authorization with ACLs or RBAC, secret management, private networking, audit logs, least privilege, schema and connector permissions, and rotation procedures. Question 17. What metrics would you monitor for a production Kafka platform? I monitor both platform health and business outcomes. Core metrics include consumer lag, end-to-end latency, producer and consumer throughput, request latency, error rates, disk usage, network saturation, under-replicated partitions, ISR churn, and controller events. For connectors, I track task failures and source or sync offsets. I also monitor freshness and processed event counts, because infrastructure can appear healthy while a downstream pipeline silently stops producing useful data. Discuss throughput, consumer lag, end-to-end latency, request latency, broker disk and network utilization, under-replicated partitions, ISR changes, errors, rebalances, connector failures, and business freshness metrics. Question 18. A Kafka consumer keeps rebalancing. How would you investigate and fix it? I would inspect consumer logs, group membership, rebalance reasons, processing duration, heartbeat failures, and poll interval violations. If processing blocks polling too long, I would reduce batch size, move expensive work off the poll thread, or tune max poll interval carefully. I would also check crashes, autoscaling churn, network instability, and rolling deployment settings. Cooperative rebalancing can reduce disruption, but it cannot fix a consumer that repeatedly exceeds its liveness limits. In your answer, cover heartbeat and poll intervals, long processing, session timeouts, consumer crashes, unstable membership, deployment behavior, cooperative assignment, partition count, and separating symptoms from root cause. Question 19. Design a real-time fraud detection pipeline using Confluent technologies. I would publish payment events keyed by account or card, validate them with governed schemas, and use Flink or Kafka streams for windowed aggregations and joins with customer or merchant reference data. Stateful rules could detect velocity spikes or impossible travel, producing alert events and audit records. I would retain raw inputs for replay, make alerts idempotent, and monitor latency, event completeness, false positives, and model or rule effectiveness while protecting sensitive data. Cover event ingestion, keyed transactions, stream enrichment, time windows, stateful rules, low latency, false positive handling, durable outputs, replayability, privacy, and monitoring detection quality. Question 20. Tell me about a data engineering project where you improved reliability or performance. In one project, a consumer pipeline processed about 20,000 events per second but developed recurring lag during peak traffic. I traced the issue to an uneven key distribution and expensive synchronous enrichment. I changed the partitioning key, cached reference data locally, and added lag and latency alerts. Peak lag fell by roughly 70%, and recovery became predictable. I documented the trade-offs, tested failure scenarios, and partnered with downstream teams before deploying the change. Make sure to structure the response with context, measurable baseline, diagnosis, technical action, trade-offs, validation, and business impact, while demonstrating ownership, communication, and lessons learned. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.